Math 230, Quest to College. I'm Joe Vasta, and today we're covering section 6.1, the product rule. So before we get into that, I'll go ahead and show you the puzzle. The puzzle says which word does not belong, so you have some words there. Lioness, network, freighter, octopus, puniness, antenna. Which word does not belong? So we'll get the answer at the end of that lecture. And let's get into counting. Chapter 6 is all about counting, and you may have already thought you knew how to count, but we're going to actually count without counting, if that makes sense. It probably shouldn't make sense. Let's go ahead and do this problem here. Joe has 4 shirts and 3 pairs of jeans. How many outfits does he have? Okay, so how we're going to do this problem is we're going to show you something called a tree diagram, which means, okay, so, Joe has 4 shirts and 3 pairs of jeans. Obviously, this is talking about me. And, so here I am. When I get up in the morning, I have 4 shirts to choose from. So I can go down this path and pick shirt 1 or shirt 2 or shirt 3 or shirt 4. Now, having picked one of the shirts, let's say shirt 1, then I have 3 choices for shirt 1. The first choice would be jeans 1, jeans 2, jeans 3. And then the same thing with shirt 2. I can pick the same 3 things. So jeans 1, jeans 2, jeans 3. Jeans 1, jeans 2, jeans 3, jeans 1, jeans 2, jeans 3. Okay, so wow, what we've just done is we've graphed it all out. When I pick an outfit, I'm traveling down one of these paths, or actually we should say up one of these paths, and this is really just a graph, and we did graph theory. Here are the vertices, this one right here, which is the root, and then we have these vertices here, and then these vertices up here, which are called the leaves, and these are really technical terms I'm using. This kind of graph is called a tree. Okay, it does look like a tree. So the question is, how many paths do we have? Well, if you counted them all out, you would see that the answer happens to be 12. So the answer is 12. But there is an easier way of doing this, and some of you probably already knew that easy way, is to say, well, we have 4 and we have 3. And what we can do with these 2 numbers is multiply them together. And so 4 times 3 is 12. So I'm required to show you the connection between graph theory, but in our homework we probably don't want to write out trees for every single problem, especially when the answer is going to be like 100 or 200. We would rather multiply some numbers together. So this section is called the product rule. Sometimes it's called the fundamental counting principle. And what I'm going to do is I'm going to write it out. I'll pause the video, write out the product rule, and then unpause it. The product rule the fundamental counting principle is written out here. Suppose that two events occur in order. And we'll just say, you know, picking a shirt and then picking a pair of jeans. If the first can occur in m ways, and the second can occur in n ways, so this is rather technical, isn't it? Then the two events can occur in m times n ways, and that's what we have here. So you don't have to like memorize this, you just have to know how to do these problems. And so that's what we're going to be doing in 6.1. It's probably going to be the most basic section of chapter 6. There are a few twists at the end of this lecture, but let's go ahead and do this next problem. It says, Joe has 4 shirts, so it's the same as up there, 3 pairs of jeans, and 2 pairs of shoes. How many outfits does he have? Okay, so what have we done? We've added in 2 pairs of shoes. So if you're looking at this tree diagram, we are actually, and I'll add this in blue, you'd have shoe 1, not to be confused with shirt 1, and we'll say pair of shoes. Okay, this is pair number 2. We'll just still call it S1, S2. So each of these leaves will now get 2 more branches coming off of it. So this is shoes 1, shoes 2, shoes 1, shoes 2, shoes 1, shoes 2, shoes 1, shoes 2. And look, I missed one right here. Shoes 1. So even though graph theory is cool to do on this, when the numbers get really big, look at this. This is very inconvenient, and that's why we like the product rule. So we'll go ahead and talk about the product rule after I draw this. Shoes 2. Shoes. But it does look like a pretty tree, doesn't it? I don't know if you would have it in your backyard, but it looks pretty cool. Shoes 2. Shoes 1. Shoes 2. Shoes 1. Shoes 2. Shoes 1. Shoes 2. You know, and if you have a roommate or somebody in your family who's saying, oh, you're just taking a dumb math class, you should show them this and say, this is what we're doing in every single problem. And they'll go, oh, whoa, wow, that's crazy. Okay, let's go ahead and do this problem. Now, you can count how many paths there are from root to each leaf, or you can just count each of the leaves. But a way of doing this is now we have like 3 events that are happening, not 2 events. First I pick a shirt, then I pick a pair of jeans, and then I pick a pair of shoes. And we're assuming that I'm going to pick matching shoes. Okay, I'm not going to get 2 left shoes. So we have this 4 times 3, so we have 4 times 3, and then this is going to be times 2. So that's 12 times 2, which is 24. So from now on, I'm not going to draw the tree diagram. But this problem right here illustrates that the product rule can be generalized to 3 events. So I'm going to go ahead and write out the product rule for 3 events so you can see what it looks like. I'll pause the video and then I'll come back and you'll see it. Okay, so I wrote out the product rule for 3 events. Suppose that 3 events occur in order. The first can occur m ways, the second n ways, the third, I was going to use O, but that looks like a 0, so I used p ways. Then the 3 events can occur m times n times p ways. And that's what we have here. So this product rule can be generalized even higher than 3. It could be like 5 or 7 or 13 or any number of events occurring in order. The other change I made to this was I put the other name for the product rule, which is the fundamental counting principle. So let's go ahead and do some problems And I'm going to not write out the trees anymore because it's going to be lots of writing because the numbers are going to get bigger than 12 and 24. So let's go ahead, go to problem number 3. A club consists of 20 girls and 8 boys. They want a girl president and a boy vice president. How many sets of officers are possible? So I'm going to do something new on these problems. I know we can just get the answer by multiplying numbers together, but I'm going to start making these little lines. This is going to help in future sections. So this first, we're going to call them slots. So, slots. The first slot's going to represent the first event, and that first event would be picking the girl president. So I'll say president. And the second slot is picking the VP, the vice president. So right under these, even though these slots seem like overkill for these problems, when the problems get more complicated, especially in future sections, we're going to really like these slots. So the first slot is how many ways can I pick a president? Well, they want the president to be a girl. And there are 20 girls, so below that slot I put 20. They want a boy VP. So how many choices do I have for VP? Well, there are 8 boys, so I'm going to put an 8 there. Because we have the product rule, we're going to multiply those together. 20 times 8. So you can think of it like 2 times 8 is 16, and then add a 0. So the answer is 160. Now imagine doing a tree where the root had 20 edges coming out of it, and then each of those edges lead to a vertex, girl 1, girl 2, girl 3, all the way up to girl 20, and then each of those vertices have 8 edges coming out of it. You'd have 160 paths. We do not want to draw that tree because it's going to be a waste of time, and we can get the same answer by multiplying the numbers together. Okay, let's do the next problem. And maybe you want to pause the video and do some of these problems on your own. An ice cream shop offers 3 types of cones and 31 flavors. How many different single scoop ice cream cones can one order? Okay, so how many events do I have? Well, I have to select a cone and then select one flavor because I'm just going to get a single scoop. So the first slot is going to be cones. The second slot is going to be flavors. Okay, so how many choices do I have for cones? I have 3. And the choices for flavors? 31. So what do we do with these numbers? We multiply them together. 31 times 3 is 93. And that's the answer to problem 4. Okay, let's do some more problems that get a little bit more complicated. But section 6.1 is a pretty short section. Shouldn't take you forever to do the homework. Problem number 5. You go to a certain restaurant. Dinner includes a salad, an entree, beverage, and dessert. Okay, so that sounds good. The menu offers 2 types of salads, or 2 types of salad, 3 types of dressing, steak or chicken, and 4 types of beverages. Well, and ice cream or pie. How many different dinners are there? So maybe you're on a first date and you took your first date to this restaurant and your date's like, wait a minute, what a terrible place this is. Well, because now you know how to count, you know the product rule, you can impress your date by doing the following on a napkin. Of course, you would have to have a pen or a pencil. Okay, so we have some events here. The first event, when you order, you are going to have to select a salad. And there are 2 types of salads. So let's go ahead and put some slots up here. So the first thing you want to do, select a salad. And then with that salad, you have to select a dressing. And then after that, you've got your entree, which is steak or chicken. So we can say entree. I'm going to say meat. So if your date is a vegetarian, I mean, this is your last date, really. And then 4 types of beverages. So I'll just put drink. And then dessert. Okay, so those we have 1, 2, 3, 4, 5 events. But the product rule works for 5 events. Let's go ahead and put some numbers underneath and then we'll multiply together. So we have 2 types of salad, 3 types of dressing, 2 types of meat, steak or chicken, 4 types of beverages, so I'm going to put a 4 under drink, and then dessert is like ice cream or pie, so I'm going to put a 2 there because there's 2 choices there. So of course you're doing this work on the napkin in the restaurant to sort of impress your date. So yeah, this map, there's an application right there. Let's go ahead and multiply. Let's multiply these numbers together. What do we have here? We have 2 times 3 times 2. So what is that? That's 6 times 2, which is 12. And then over here we have 4 times 2, which is 8. So I'm going to multiply that together. There's many ways of doing this. You could say 2 times 3 is 6, 6 times 2 is 12, 12 times 4, and or you could just do it this way. So 16 and then 8, 9, carry the 1. So 96. That's how many different dinners there are. And so you can then turn to your date who's not impressed at the restaurant that you guys came to, and you can say, hey, look, there's 96 choices. And if you wanted to go dry on the salad, there's even twice as many. But that wasn't given as an option. You have to do it this way here. So the product rule is very useful. It helps us count different things. We'll be counting more applicable things in the later sections. These problems that I do, and I think there's only going to be 7 problems. They're kind of silly, but just go with it, okay? It's not super difficult to do these problems. The top shelf of a bookcase contains 3 comic books and 2 coloring books. The bottom shelf contains 4 comic books and 6 coloring books. How many ways can you select 1 comic book and 1 coloring book? Okay, so this problem 6 is a lot more complicated than the previous 5. What we want to do, perhaps, is to draw the bookshelf. Okay, so we're going to make a bookshelf. Bookshelves, and it says the bottom shelf contains 4 comic books, 4 COM, and 6 coloring books, 6 COL. Actually, I should have done the top one first. That's the first sentence. The top shelf contains 3 comic books and 2 coloring books. Okay, so that's what it looks like. Hopefully I drew this diagram correctly. I'm not going to draw all the books. And it says, how many ways can you select 1 comic book and 1 coloring book? So your events, you're only going to have 2 slots. The first slot is for comic book, and the second slot is for coloring book. So because I drew the shelf, it makes it a little easier. How many different comic books do you see on the shelves? Well, there are 7. How many different coloring books? Well, 6 plus 2, there's 8 of them. So I have 7 comic books to select from and 8 coloring books. Well, these are my 2 events. I'm going to use the product rule, multiply them together, and my final answer is going to be 56. So you got to be careful that you're not just going to select all the numbers like 3, 2, 4, and 6 and just multiply them together, because you would get a really big answer and that would not be the correct answer. So the problems near the end, you're going to get a few like this, and you just want to just slow down and maybe even draw a picture. I have one more problem that's going to be done like that. Problem number 7, so it might be worthwhile to pause this video and see if you can figure out the answer to this problem. There are 6 different ornaments on Grandma's Christmas tree. In her attic, okay, so this is getting a little scary. She has 8 different holiday pot holders, how exciting, and 4 additional ornaments. How many ways can her grandchild select 1 ornament and 1 pot holder? So maybe that's Grandma's gift to her grandchild. Like, you get to have 1 ornament and 1 pot holder. Lucky kid. Okay, so I'm going to go ahead and draw Grandma's Christmas tree. Okay, so some of you might be laughing. Here's the disclaimer. I mean, I'm not an art teacher, so if I was, I'd be doing that. So here's the, trying to make a star. Oh, great. That's my star on top of the whatever. Okay, so on Grandma's Christmas tree, she has 6 different ornaments. So 6, and I better abbreviate, O-R-N. Okay, now where are we going? Oh, to Grandma's attic. Okay, so her attic, let's just say her attic's up here. There's her attic. Okay, so that, I should label that. This one I actually should label too, because some of you might go, that's a tree. Okay, so there's a tree. The attic. What does she have in the attic? 8 different holiday pot holders. So we'll just abbreviate 8 pot holders. And 4 additional ornaments. Oh man, this looks bad. Looks like Grandma is growing pot in her attic. These are pot holders, okay? So it says it right there. So we have the tree, we have the attic. We have the grandchild, which I am not going to draw, and I'm not going to draw Grandma either. Or the rocking chair, the television that she watches all day. No, we're not going to draw all that stuff, but we are going to put our events. Her grandchild can select what? 1 ornament and 1 holiday pot holder. So there's 2 events. I'm going to multiply 2 numbers together. The question is, what numbers go under these slots? Well, how many ornaments are there? So look around on this picture. There are actually 6 here and 4 there. So there's 10 ornaments that the grandchild can select from. Grandchild can only select 1 ornament. How many pot holders do you see in this picture? Well, there's 8 of them. So we're going to go 10 times 8, which is 80. Now here's the deal. As we get more and more into this chapter, these problems might change to how many ways can her grandchild select. 3 ornaments and 2 pot holders. And that's actually a lot more complicated than what we're doing here. And that would involve something called permutations or combinations. So we'll get into what those things mean. So that is all there is to section 6.1. We'll come back to the puzzle. Which word does not belong? Okay, so some of you are going to get rather upset when I show you. And some of you may have figured this out. Look at these words. All these words, except one of them, have numbers in them. Does this red pen work? Yes, it does. So lioness has 1, and then this one has a number in it too. 2, 8, octopus. I'll come back to that. 9, 10. So the word that does not belong is octopus. That concludes section 6.1. I'll see you in the next video.